I recently did Andrew Ng's deep learning course on Coursera. It was really good, and I'm sort of halfway through it. But one step that really helped me to understand it was to build some of the models in Excel. And this is a model that is going to try and program itself to find a function that distinguishes between red and black dots, just spatially, x and y, just why they're x and y. So that's one neural network that's learning. And then there's a copy of that that looks at what it's learned, and it colors all of these pixels. So if I run this, it starts off completely dumb because the learning algorithm on that sheet, the model sheet, trying to distinguish the reds and the blacks, has no idea because it's got very untrained parameters. But with the beauty of gradient descent and backpropagation, it can minimize this cost function, which is basically saying, is this red? Do you think it's red? And it looks at the difference between the two, and that's the cost or the loss. And it's trying to minimize that, and it minimizes that by taking that loss function and backpropagating it through the network to incrementally, slowly edge the parameters that it's learning and the functions that they represent towards something which will accurately distinguish between red and black dots. Now the loss function is down at 28, and you can see this curve here, which is the number of iterations, 200 or something, and the rate at which the learning curve is coming down, because you can see it's starting to be able to distinguish between the red and the black. Now that learning rate's quite high because at some point the step that it moves, the step that it closes the loss function with, is going to be too big for the functions it's in. It's going to start skipping about. Again, I would suggest looking at Andrew Ng's course for a description of neural networks and gradient descent. He is a genius, whereas I've just learned. But putting in Excel has helped me. So I'll build it from scratch because I think that's probably the best way to do it, which will mean I'll have to generate data. Because as you can see, there are two circles. There's a black circle and a red circle, but there's some sort of scatter on it. So you as a human, a programmed, evolved algorithm, were able to spot very easily that it's two circles, and actually it's the area between the two, the border between the two could differentiate. But it doesn't know, so we need to make some random scattered zeros, dots, and I've got 150 dots in each circle. Oh, look, it's dramatically speeding up as the neural network that's learning the model sheet. Slowly, the function that it's building is closing in on a function, or a very complex function with lots of inputs in all the hidden layers. But it's arriving at a function that separates the black and the red. So that's progressing exceptionally well, which is quite unusual because it would normally take a bit longer. And to iterate, and then to iterate with this learning rate, you'd expect it to probably go crazy. And there's indications that it's starting to flip out because the learning rate's too high. So we'll just wait to plot those 50 points to show you what happened to the loss curve. Yep, okay, and let's escape from that. So there you go. That's as far as we could learn with that learning rate. It may have improved actually as it went on, but if we'd reduced the learning rate, we would have represented this perfectly. But let's start building it now. So I'm going to get a new sheet. I'm going to close this other one because it's going to slow everything down. And we are going to probably need to see a lot of layers, so I'm going to reduce the font down to 8, and I'm going to kick off with the sample. So that's 1 to 300. Plus 1. It's a bad start, I would thought, to the programming, the fact that we want a series of 300. Now I'm aware that there is an Excel fill tool to do this, but I'm just not very good with it on the quick keys. So probably about here is 300. Oh, but that's not such a disaster because I've now got a formula that I can copy across. And you see it's not updating. It's not updating because we crashed out of the code on the previous model, and that left us in a non-calculating state. So D, I've got that. Those are my nicely colored numbers. Cool. And now we want some circles to represent that. So the circles, we're going to have a total of, well, let's think. How would I like to do it? Well, it's 150. 150 dots per circle. And the radius of the top one is going to be 4, yeah. The radius of the top circle is going to be 1.1. The radius is of the inner, the red circle, is going to be 0.9, and I want to have a scatter on those dots of about 0.15. I have looked at these. I wonder what 0.1115 means anyway. We want 1.5. So now let's figure out the x and the y coordinates of these dots and the color. Okay, so the best formulas for making this is going to be equal to sine of 2 times pi, 2 pi r. The circumference of the circle is 2 pi r. 2 pi r. And I'm going to multiply that by the number we're looking at, divided by this number. Actually, okay, let's think about this. Divided by I'll call it cases. So I'm going to have a named constant called cases, and I'm going to divide that by 2 because I've got 2 circles. Now let me try and explain what's gone on here. So come out of that. It won't like it, but here I'm going to put 300 because that's the total number of cases, because that's quite useful. Alt-IND, new cases. Yeah. So that's the number of cases. Close. Good. So now that's working. We would like a random element added to this. Oh, hang on a second. We've got no radius dimension. So let's multiply this by if the number above 4 is less than cases divided by 2, then I would like to use that radius. So black first, F4. If not, I'm going to use that one, 5. Cool. So I think that's going to do it, but I also want to add a random scatter. So rand of this random constant f, rand times this constant f4 minus the same thing, f4 divided by 2. Cool, I think that's it. And then the y is exactly the same as cos. That's kind of nice and easy. Cos. Yep. This is equal to, if the number here is less than that divided by 2, then 1 else 0. Okay. Yeah, right. So now we should be able to swing this over for all 300 points, and we should get 2 circles out of this. It's a bit annoying that I can't scroll to the end, so I'm going to put just a space in that last row so I can do this. So looking pretty good. It may be worth actually showing you how you would do this as an array, because that's quite useful. So I'm not going to use that. I'm going to use the full array. Likewise, I'm not going to use the The individual numbers will use the full array, but everything else is fine. So that's good. So that's programmed as an array. That's programmed as an array, which is interesting that it is different. Yeah, because actually if I'm going to program that as an array, then I think I'd better make this fixed. Okay, so here is the x, here is the y. Which is odd that they're not exactly the same number. I think I'd better investigate that fairly quickly. No obvious reason. Yes, a very obvious reason. Which is that there's a random component in it, which I just added myself. That's a little embarrassing. Okay, so we've got the random in. We're going to put cos, and that changes the whole thing. And then here, likewise, we're going to do an array. Arrays are really, really useful when you're building neural networks in Excel. I have determined. So good. That's a pity. I didn't really want those dummy numbers. Let's be clean and get them right. This is the penalty of screaming through the screen, putting a space at the end of the plot area. And I really better hurry up, otherwise I will justifiably lose your interest. Okay, so put that back in now. Put the O as BL. I'm highlighting the whole area if you're not familiar with arrays, and I'm pressing Shift Control Enter to enter the array. And that's effectively it. So I want these on a cross plot, so I'm going to need to know whether they're red X's or so let's have the black ones. Black, black, red, 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 red. If good grief. Right. Equals. If the row above, that's the color. If that F4 is equal to, let's put a cell there that says what color it is. Then, so if it's a 1, then I'll take from these two. Yeah, F4 too. F4. Else, NA. Because NA doesn't show up on cross plots, which is quite handy. So good, that's 1. Oh yeah, it thinks it's a 1, so I'll make that a 1. Make that an input effectively, because then we can change it in the event that I've got the wrong color. And that is equal to not that. I think I should do. It's a calculation. So let's just copy that formula down. I've done it again. Copy. And just see if it's in the right thing. Yep, appears to. It doesn't like it's false. I'll just put 0. Okay, so have we got dots? Yeah, we've got the good looking dots. So now I'll try and get these on a cross plot. How annoying. I'll put, I think it thinks that I'm trying to insert scatter dot, delete, delete, Control Z. Yeah. How embarrassing. I do not want that. I want to insert just a scatter plot. And it's being very annoying. So select data. Is it a row column switch? Maybe. Discomfort popping over the microphone. Delete. Close. Right, select data. I'm going to add a series. It's going to be called black. And the series of x's is going to equal the top row. And the series of y's is going to equal the next row. Okay, and I'm going to add red, where the series of x's is going to be that, and the series of y's is going to be this. Okay, so let's give us a chart. Well, great, and they all work. But this irritating version. Well, you saw that I just deleted it, so I've rebuilt it again offline. I don't like this version of Excel. I think it's 2010. I want to alter the markers. I want built-in, and I'm going to leave that as a circle. And I believe I've picked up the red one, so I would suggest red, which is marker fill, solid fill, red. Marker line color, none. Okay, it looks a little big to me. This one is going to be black, so marker options, round. I think we're going to need to go smaller, sort of 5. Marker fill is solid fill, and this is black. Marker line color, I hope there's none. Okay. So there we've got a chart. I don't like the axes, so I'm going to fix them, the scales. I'm going to have the axis labels low, so they're out of the way, and I would like grid lines. Maybe this is it. Inside. Okay. No, that didn't do it. So let's try again. Format axis. I haven't used this for a while. Grid lines. Where would you see grid lines? Okay. I'm going to have to pause. Well, of course, it was blindingly obvious. So I want grid lines on here. Major grid lines, solid line. Color, okay. I didn't seem to get that axis. This is the one I want, major grid lines. A bit too harsh. This is very cumbersome. Such is life. Close. Okay, so I've now got grid lines. And I don't really like this chart with a fill or a border. And I'd like this somewhere else, this whole chart. So I'm going to take it away and put it on a dashboard, which we'll we'll use for other stuff, you know, the input commands, etc. And I think I'd probably better fix this axis to, I don't think I set the x-axis to a maximum. Okay, close. So that's the dots made. That was quite dull. I apologize. So we go back to our neural net tab, and now we're going to start doing some of the interesting bit, which is the real work. So in the event that I die, I'm afraid you'll have to get it from another video. But in this instance, let's see what we can do. I'm building a neural network which is 10 neurons deep. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's two dimensions wide initially, because you know that's the that is the multitask. that's the dimensions of the input, which is an x and a y. There are dimensions to it, and there's 2. So the first layer needs to look at each 2. That's the x, and that's the y. The 2 components of the input, and these are going to be a set of blue numbers centrally located. And I'm also going to need an offset, because we're going to do this kind of y equals mx plus c formula, and this will be b. So this is going to be b1. This is going to be y equals mx plus c. This is the equivalent of c1 of c. Sorry, b. So let's call it b1. And I'm going to initiate that with zeros, because that is the way to go with the offset. For the parameters, you need to initiate them with something. If you don't initiate these with something, then it won't start. You start it with 0. And one of the best starts is normal inverse. Yeah, thank goodness this function is available in this useless software. That's the normal inverse of a random number between a unit normal random, and it's going to have a mean of 0 and a standard deviation of 1. Now there's this fancy sorry, there's this fancy boost that you give to this square root, yes, square root of 2 divided by the number of neurons in the previous layer, which is 2, because the previous input has got an x and a y coordinate, and that is our initial set of inputs. That's how we set them. So now we need to do effectively the z bit. So I'm going to just take a block of data that's about the right size and pop it there. I'm also going to freeze the pane here, so that we don't have to keep darting all over the place. And I'm going to put a little extra space in. I'm going to call this one z1, because this is the function y equals mx plus c that we're doing on the inputs. And the way we do that is equal to oh gosh, goodness me, maybe I need to think slightly. Matrix multiplication of the weights, the m's, times all cases, because we're going to do a batch view which does all of these together, and it's going to be plus the offset. So that's layer 1, linear function in, put a little border around it, and now, although we'll build it here, we need an activation function here, which is going to be which is going to turn this linear function into a nonlinear function, and we're going to use a ReLU, which means that we're going to say, we're basically going to chop this linear function in half, and if that is greater than 0, then 1 else 0. That's it. I know I can't enter that as part of an array, so I'm going to take that, copy it, kill the thing, and put this in one by one. I didn't think I'd entered an array. Let's try again. So what I'm trying to do is, one of the big advantages of arrays is that you can enter them as blocks. It also makes it a little harder for people to mess around with it. Oh, I've got the wrong thing. I've actually got the derivative of a ReLU. What I actually want is not 1, I actually want the value itself. So that was you will need the derivative fairly soon to see how you would backprop that. Alt S, formulas. Great. So now we've got in lots of activation functions, and we've got the linear bit. So that's layer 1. Right. Whew. Now layer 2. Layer 2 has got to, this is important, this is what I think was a real help for me in Excel, was to be able to see how these lay out. So I want a 5 neuron wide, 1, 2, 3, 4, 5 layer, and this will multiply by the output here. I'm going to move B over a little so that I can squeeze one more of these in, and I'm going to go for B2. So the inputs, the offsets B2 are here, and this is going to be my W2. 1, 2, 3, 4, 5. Okay, so you guessed it, Z2. This is the linear function of the second layer, and this is not too well laid out. Pardon me. Okay, so I just want the space there. So Z2, Z2, and Z2 is equal to matrix multiplication of the weights of the current layer times. Now, this is where you can see that the layers join. So we're multiplying it by the output of layer 1. So instead of looking at the input, we're looking at the output of layer 1. And we're adding on the offsets. We've entered too many elements for this function because it doesn't need a multiply, it needs something else. So that's interesting. Why did that bust? Let's have a look. Probably because I didn't have a number in there. Yeah, wow. So that's quite handy. So I must have worked out my numbers. Okay, so that's Z2, and the activation function for layer 2 looks like this. Oh, A2, and it's F2. Pity. Nearly had that laid out quite neatly. So it looks at its own layer. Copy. Oh yes, formula. Put a border around it. So that's the activation for layer 2, and you guessed it now, layer 3. Layer 3 is going to be 5 wide to match the sorry. It's going to be one wide, but the parameters are 5 wide in order to multiply with the previous layer, and the B3 component here is 1 wide, B3, W2, W2. I don't like the spacing very much. Okay. So this is it. We're actually effectively have built a neural network. Within about a minute, it will be built. Let me explain why. This is a forward prop, fully connected network. At the moment, it's not got backpropagation in it. I wonder if I can just stretch these. I think you can use Excel like knitting with the F2 function, which is pretty good. And I need to make sure I'm looking at the activation functions of layer 2. And I need to call this Z3. Z3. Okay, so the output of Z3 is, well, because this is a kind of binary classifier, again, I'd refer you to Andrew Ng's notes. We're not going to use this easy function, as it were. We're going to use a sigmoid, which is a little bit more mathsy, but it's just genius. 1 plus the exponent of the z, which is minus the exponent of z, minus and a bracket. So there's my sigmoid function for the output. Now, what that means, what A0 is doing, that's effectively the guess in each case as to whether this input is a black or a red. So that's its guess. 40% chance that it is black, 83% chance that it's black. But it hasn't got a clue because these are rubbish parameters. Let's initialize these properly. As I said, this weighting of the okay, so I'm going to try and change the whole array to divide, or effectively to reduce the weight by the number of neurons in the previous layer, and the papers by a guy called he et al. So he and the other people. This one is going to be divided by 5, the neurons of the previous layer. Okay, so hopefully I've got that. So yes, I've got the right weights. We're ready to go. I need to call that capital W3. Yep, naming looks good. So we are effectively, I'll get rid of X and Y because we know what that is, and I'll just call what the array is. That's W 3. 1. Whew. This is the neural net. And we need a loss function, which is going to show you so the function that we're going to backpropagate against. So this is quite important, and just remember, it's quite an almost frightening looking formula, but it's not really that bad, and it equals the truth, if you like, which is it black or is it red, times log of the guess, plus 1 minus the truth times 1 minus the log of the guess. Yep, that should be good, I think. Let me just think about that. 1 minus a log. That was a bit frightening. Sorry about that. So I think we've got it working now. 1 minus log. Yep, looks good. There's my loss function. And the cost function that I'll plot, which we saw on the previous plot, is the sum of that. And this is where it might be quite handy. It's equal to the sum of the loss function divided by cases. That's the number of cases. Knew it would come in handy. And that's a J. And that's a L. Okay, so now we've got a neural network ready to go. I'm going to slightly rearrange this, if you'll forgive me, because we could put the backprop in now, but then I can rearrange it later. Yeah, okay, let's put the backprop in now. So the backprop is going to look at the cost function, and it's going to find out the gradient of that as it moves backwards through, backpropagated through the forward function we've got, where the output layers go into the outputs of the earlier layers go into the inputs of the later layers. It's going to backpropagate that and give us the magical backpropagation, which is going to grind to a final result. I'm going to pause for 1 second. Okay, carrying on. Right, the backprop, we have a working neural network, is I'm going to stick it just below the output layer of layer 1. So this is going to be called DZ3. And DZ3 is the derivative of the sigmoid we saw in A, which is quite simply the guess, A1, minus the truth. Yep, that's it. We need to backpropagate that into the constants, into the to find the gradients of these weights. That's right, yeah. So this is DB3, which is nice and simple. It's equal to the sum of that divided by cases. Divided by cases. Cases. This version of Excel doesn't present things in the way I'm used to seeing. And the W's are black. That's equal to the dot product mult. Oh, at last. Of the DZs that we just calculated by the transpose. Yeah, I think I got it. I think I understand this irritating by the transpose of the output of layer 2. Cool. Dear me. Okay, so now we need to stick in a DZ, so I'm going to take a copy of this A range, stick it in here, and call it DZ. One another space, DZ. DZ2. DZ2 is a bit more complicated, but it's not too bad. DZ2 is equal to the matrix multiplication of the transpose of let me think. One sec, I'm checking, I can't remember. Of Z2. No, transpose of the actual W weights, transpose, comma, of the W weights by Z2. And it would prefer some brackets in the correct place. And obviously I got something horribly wrong there. So let's see what it was. Don't see why that would crater unless I one sec. Terrible. Embarrassing. Sorry about this. As I did explain, I'm new to neural networks, so these are not actually intuitive to me yet. So it's DZ3, but we also want to multiply that by the derivative of a ReLU, which is if Z2 is less than 0, then 0 else 1, which is the derivative of a ReLU, and that worked great. Okay, that should make the rest easier. Now we need a bit of space for our these parameters. The heat is building up in the day here in Goa, and it's getting quite hard to write anything, but I'm going for it. The B's equal to the sum of DZ, these derivatives, divided by cases. I need to enter that as an array, quite annoyingly. the gradient. Yeah, I'm trying to look at the formulas I wrote on a much bigger model that's got other optimization in, and it's proving a little difficult. So this is equal to the dot product of A1 and the transpose of transpose A1. Let's get this right. 54, I think that's that. Transpose is equal to awful, this is agony. It's a matrix, okay, it's a dot product, and it is dz dot product by transpose of A1. Divided by cases. As you can see, the heat of the day is getting to me, and I seem to be making quite a pig's ear of that. LC, I don't like that LC. I'd extended my range too far because of the silly space I put in to save time. So now finally, DZ. So DZ is going to come in, I'm going to use this actually, because it's got parameter space for me. Copy, and that's going to go below here. And we're going to call that DZ1, DB1, and DW1. These are going to be black. Let's try and do this first, given that we made such a mess of it last time. This is going to be equal to the dot product of dz and the input in this case, which is the, well, it's input, divided by cases. LC, I think it's the LC sucker again. Yeah, great, it was. Okay, and dB is equal to the sum of the z's divided by the cases. And finally, dz, we are nearly there. This is the last piece of wiring before we have a fully backpropagated neural network. And it's presumably it's the dz2. So we are going to first of all take the weights of W2 equal to matrix multiplication of the transpose of weights 2 with dz2 multiplied by the derivative of the derivative of the ReLU. So it's going to be A1, I guess. right? Can that be right? Z1. Pause. The derivative of the ReLU is this function. If that is less than 0, then 0 else 1. Which does make me wonder slightly whether I goofed up the previous versions of this. That's dz and dz2. Yeah, that looks good to me. And dz3. Ordered symbols prevent you grabbing the stuff you want. So to my mind that looks good, but I've got some values in there. So let's just figure out what I did wrong. I presume I just forgot to transpose the second bit. Yeah. So I had the arrays just facing each other the wrong way. So I think that's a working neural network. Now, from this point, what I'm going to do is I'm going to jiggle it around a bit because it just makes it a lot easier in Excel if you're able to stamp all of these inputs together. So I'm going to put my Z1 up here, just above the A, and I'm going to put my W X just below this. And I'm going to call this chunk of data from here to here the parameters. Alt-IND, new params, okay? Close. And I'm going to copy this because I've got a lot of live formulas in here to initialize it. And I'm going to stick these somewhere sort of safe down here because we'll use these again. But in this instance, I'm going to call Alt-IND, Alt-New, params, initialization. Because we only want these values at the very start. So I'm hoping that's by 2, by, well, I know that that's going to be by 10 neurons. And I know that this is going to be by 5. Rebuilding a neural network in Excel is obviously much more painful than Python or the proper software that you would normally do it in, TensorFlow Python, where you would just flip a digit, but here you have to reconstruct the whole thing, so it's quite a pain. But it's very static and you can see what's going on, which is my argument for why I'm presenting this offering to you. Okay, so here's the initialization. And we've got 2 arrays that are named params and params in it. And now I'd quite like to have an update. So I'm going to make space for an update. And the way I'm going to do that is I'm going to jiggle it even more. I'm going to put my A's just below the each other. A1 here. So all I'm doing is cutting and pasting the stuff that we wrote. But I think it was easier, I hope, to follow with it later, as it were. But for Excel, you kind of want to reduce the stamps. You want to reduce the kind of areas that we're going to pop over each other, particularly when your Visual Basic is as appalling as is mine. So I've got some space now. So this is going to be our parameter update. And I'm going to say, make this, this is equal to, and this is what gradient descent's about. This is equal to the old parameters, yeah, minus the learning rate. We don't have a learning rate, so learn rate, I'll make one up, times the derivatives here. So this derivative gives you the way you're moving down the curve. So on the dash, let's pop in learning rate. Let's get rid of the grids. Learning rate's an input, and it's going to be where do we start off before? Probably 0.25 or something. 0.1. Let's call it 0.1. Call it the learning rate. Dyslexia and fat fingers. Okay. Alt-IND, new, and I think we're going to call that learn rate. Great. So now we've got a learn rate. So that's going to give us the ability to step through. I'm going to extract the cost function here as well, because we're going to want to plot that. So this is equal to cost, and again that's gibberish at the moment, but hopefully it won't be soon if we go back to the neural network and we call this thing cost. Alt-IND, new, cost. So we've got a cost function that's showing through on the other side here, and that's what we're going to try and optimize. Cost. I think Andrew Ng suggests that you call it cost if it's the sum of a batch. And we need some iteration numbers, iterations. Now, there's a nice way I could show you to do this without using any VBA, where you switch the iteration code on Excel and you let it press F9 and it just iterates. But it's a little bit clunky in that you can't see very well what's going on. I'm Spain the neck. So 1,000 iterations. Alt-IND, iterations. Cool. And I'd like an area to put a print of stuff in from, say, 1 to 1,000. 1 to. Let's try if in this version of Excel I can use this irritating grab handle. No, can't. Well, I think I've got about 1,000. Nearly 1,000. So that's the case. I'm going to name this area beside it results. So we can step through the learning curve and kind of record what's going on. Okay. Cool. I would like this to be percentage and blue and with a boundary, and I'm going to stick it in the middle for neatness, and there you go. So we've got somewhere to put the results. Results. So that's iteration. And we've got a cost function to look at. I'd like to have a bit more space to see what's going on. Let's put a curve or a chart up. Let's see if this irritating scatter plot works this time in 2010, or is it just going to drive me nuts? I think it did. I think it worked, so I'm going to go with that. To about there. Pick the series and call it results. Or better still, loss. Cost. Oh dear, 54 minutes. So I think we're ready to go. Now we need the tiniest amount of VBA, I'm afraid. And that VBA is really reasonably simple. We need one more named parameter for this. We need a parameter that Okay, one more name parameter, which is going to be the range of updates. I don't like these zeros appearing, so I can format them, format cells, so that they don't mess up the screen. It just makes it easy to see what's going on. And I'll colour all loose ones, because remember we're stamping these arrays just as a block, and I should imagine it will mess that up on the first stamp too. And I'm not sure what's going to happen to these numbers, but let's kill them anyway, because we know the size of our layers. Backspace. Control D, get rid of it from above. What's this? Ah, right. I'm using the format badly. Where would that have come from? Would it come from above? I should be doing this offline. But it's taking seconds, as you can see. Well, more than seconds. But clearly, the beauty of the spreadsheet, or the clarity, is something that's ingrained in me after goodness knows how long I've been making spreadsheets, and it's going to make life easier. Okay, so I've got parameters, and I need a parameter new. Okay, so this is yep, Alt-IND, Alt-New. That's the gradient. That was really a nasty mistake. This is the update, so let's call that update. Params update. Copy. Okay. Crumbs. Right, ready to go. So, as I said, we can do this with VBA code. So Alt F11. Insert a module. Oh no! What on earth is this? Import, insert a module. Oh yeah, okay. Sub initialize. And so when this macro runs, it's going to go range, and the range we're going to fix is the, what is it? It's the params. Params. And they will be equal to, or they'll be made equal to range. I think I've got this word in my paste buffer. Yeah, params update. No, it's params init. Init. Or init. There's init. Init. Dot value. And also, I'm going to set the range of the printed results that we put in to results. It was called equal to 0, or NA actually equals NA because they then won't appear on the crossbar. So that's our initialization. However, I guess I have I've given the initialization the wrong name. Oh, did we honestly not name it? Look at that, how sloppy. I've named it with a W at the top. So Alt-IND, manage the names. So params init, I want it to start at 87 instead of where it was, and I want to copy that name. Copy. Okay, cool. So back on the VBA, that's in. And now we want a subroutine to learn. And this is going to be called learn. And this is going to make params equal to params update. Again, params update, yeah, I got the right range there. Params update.value. And that's going to do for a loop of iterations. So for x is equal to 1 to range iterations dot value next x params update results dot cells. Well, we want the row to index according to x, and it's column 1, and I want it to be equal to cost. Cost dot value, I suppose. Cost dot value. So that should give us the steppy approach that we're looking for. So let's see if it works. We don't have an underlying thing, but we do have a cost function. So we can't see the results of it yet, but this may be dragging on slightly too long. And assign a macro to it. Command button object. I don't even know what's going on. Insert a macro button. Assign a macro called learn. Rename it as learn, and then press the button. Presumably it won't work. Oh wow, it is working. So we're seeing the cost function stuck at 30, which kind of might indicate that there could be miswiring in it, and I should really have checked. And it's zipping through iterations as we speak, stuck on 30. So that implies I've got a bug in my code. So I'm going to let it run, see if it prints, see if there is a change, and then fix the problem. But I will do that offline because I've taken an hour of your time, and I'm reluctant to take any more. These iterations are quite slow. But we saw it whip past the first 100, so we must be close. But the fact that it's stuck on 30, yeah, not sure. Okay, flat as a pancake. So there's a bust in the model. So let's have a look quickly and see if we can fix it in seconds. So the update, well, that's good. It's looking at the gradients, but the gradients, divide by case, divide by case, divide by case, divide by case, not divided by case. I think there is the problem. So the derivative W3 wasn't really quite right. Now let's put in an initialization macro. So assign macro, initialize, okay, and call that initialize. That's good. And now let's try 500, because that was a bit lengthy. So we're running 500 iterations. We're hoping to see the cost function go down to see if that was the bug. But again, it's looking stuck. And this will be annoying if I've subjected you to another run of a broken neural network. I will fix it properly next time. Give it 10 seconds. Oh, no, look, it's flickering. So the fact that it's flickering is odd. I'm going to explore what's going on. Oh well, so apparently it is working. It's just taking quite a while to stabilize. Oh, I don't like these dots. So marker, again, subjecting my audience to this. My apologies. It's very jumpy because I think this data is still random. If I F9 it, you'll see the random components making it work. But I'm going to carry on like this because it's quite interesting. I'm going to set the learning rate to about 0.2, and I'm going to initialize it again, and then let's run it and see if it has a better start. And surprisingly, this computer is still too slow to represent the curve in real time. I think I need to slow down the code on this computer such that it updates the chart fairly regularly, but I may need outside advice to get that to work. Okay, look, great, learning curve's on. Cool. So I'm going to now color the area so we can go right the way to what we said we were going to do, which is to make the two neural networks that do this same thing. So let's start on the second one. Now, you know, this is going to be much simpler because we've already built it. So what I'm going to do is I'm going to move copy sheet, put it here, and I'm going to call that the move copy and make a copy. And I'm going to put that here, which is, I'll call it neural network 2. I quite like that. But I'm going to get rid of all the bits I don't need. And all the bits I don't need are basically all of the backprop. So that's the DZs, but I'm going to, and I don't even need the loss function. Delete, Alt-D. Okay. So I'm not going to be updating this. So I'm going to wipe that out. And I'm not going to need to initialize it because I'm going to take its value always to look at params. Now I would, I've still got named ranges on this page, so Alt-IND. Let's get rid of the named ranges on the neural network 2 because I don't need any of these, and then to delete. Yes. Okay, so that's nice and clean. So what I'm now going to do is I'm going to make these equal params, which was the name we gave to the parameters on the other sheet. So now this neural network is just looking at the stuff that was learned from the previous neural network, but we need more cases. So this is all programmed as arrays, so I'm going to have to bust the arrays in order to just stick in some rows that will so some additional columns that will allow us to put enough pixels on the screen, and that you can't insert a column in an array, or at least not I'm aware of. Please, if you know that, teach me how to do it. It would save a bit of time here. You can edit an array by poking your finger anywhere in it. And now I need 2,500 additional rows. So let's stretch this out to here and find where 2,000 rows is. Where must be a quicker way. 2,500 is 50 times 50, which is enough pixels to cover the screen. So here we are at 2,500. Let's get rid of all the rest. And now let's take this chunk of code or space that we made, which was an extra, well, beyond 300, it would have been 2,200 columns. And I'm just going to bung that into here. Can't change part of an array, so I've still got an array, which is annoying, which is that one. X, move it in, just in, still got an array. So I'm looking for curly brackets. If I see any curly brackets down here, then it's those curly brackets that are causing the problem. And it's that, it's the sigmoid on the last one. Delete. Cool. So let's try again. X, cut, and then insert here. It's quite irritating, these. Let's get the numbering right. Copy V. And we're going to extend all of these formulas. So this is going to be equal to, but I suspect LB is not the right number, really. Oh, these don't matter anyway, because these are currently rubbish. This does. We want to get out to CR. So let's just build the rest of the network with CRR in mind. CRR. Highlight the full array, equals CRR. Next one, highlight the full array, equals, I don't think I've got highlighted the full array, equals CRR. This is just extending the arrays out to catch the new much bigger number of cases. So that's the Z's right. The A1s, the A2s, and the sigmoid. CR. Okay, this color coding is good. It's now going to say if okay, great, that's one array. So if the number at the bottom, well, it's no longer the number at the bottom we're really interested in. We're interested in A0. If A0 is greater than 0.5, then take the stuff above, else NA. And similar here, equals if A0, sorry, A3, the final output, if that is less than 0.5, then that would be the red. So those are both in place. I think we're ready to go, other than the fact that we do need some numbers. So these numbers are, can I do this as an array? This is going to be interesting. Well, we need to cover 50 pixels. So 50 pixels square, and we need to, we've got 1.5 as the starting point, and we'll go down to minus 1.5, that's the range. And then we need a step, which is going to be equal to that times 2, because we have to cover the full area. Divided by actually 50 minus 1, 40, because there's 49 increments between 1 and 50. Great. And that doesn't exist. Okay, so the formula I want in my x's, these are the pixels going across the top of the screen, is equal to 1.5, that's the start point, minus the step times mod, so that's kind of truncating, or is mod the remainder? The mod is the remainder. Anyway, of the numbers, down to 2000. Yeah, I'm going to have to change that final number of the numbers. Divided by 50. Okay, that's promising. Let's fix that last digit, 2,500. And the y is equal to, again, the step, because we're starting at plus 1.5 minus the step times an integer. So that this is doing the truncation, an integer of the number divided by 50. Yeah, divided by 50. That's interesting. I think I have to use the integer function slightly better, but no, maybe not. Divided by 50. Great. Well, I think those are my pixels, and I'm not expecting to have any more, but this doesn't seem to have worked very well. Oh, because we haven't filled this out. So, is this going anywhere? No, K doesn't go anywhere, because we're now referring to A0 as our choice. So, I think we can delete that. Nevertheless, why would these not show? Oh, because we've got an LB in here, CRR. Odd that they should both have gone. Let me determine why I'm losing these. No, I've gained them. So yeah, I think we've got some color. Okay, so now I need to put these on the on our chart. So I'm going to add some data on neural network 2, and this is going to be the black. I'm just going to see if I can get out of this irritating, unhelpful help screen. I'm going to call this black tile, and the series is neural network 2. Not letting me grab the screen. Let's try again. Select data. Add. Black tile. Oh, doesn't let you grab outside the freeze. How annoying. Try this one. So I think I've got the black tiles. Seems like a good start. And now I want to add the red tiles. Network 2, red, and is the Y. Right. So why would these be as useless as they appear to be? I've obviously got some only portion of it showing, but let's format data series. Let's make the markers a tile, which should be that option. 7 looks all right. And the color, I think, needs to be marker fill needs to be a bit lighter, otherwise we won't see what's going on. So we'll have it that sort of blue. Oh gosh, marker line color, no line. Close. And then format data series. This one is primary marker built in. Let's have another one. Let's go for marker line color none, marker fill, solid fill, and we'll have that sort of orange. Cool. Close. So now we're looking pretty good, but for some reason it's bust. So I need to find out what's going on here. And I think it would only be fair for me to stop doing this while I figure it out. One sec. Well, of course, I'm sure you already spotted it, but I've stopped the check at the earlier column, the shorter neural network column. So we're going out to CRR. Same here. CRR. Okay. So I think that's right. Yeah, look at this. Okay, that's an interesting start. Okay, so let's see how it learns from here with another 1,000 iterations. So we're half learned, but if I continue learning from this, it's gonna overwrite this chart. So it'll be slightly annoying. We'll lose the initial curve, but we'll get the next 1,000 iterations coming down from here. And we'll see if the boundary diagram is doing the right thing. This is quite an old computer. I'm using various friends' computers at the moment, which I thought might be faster than mine. And they are desperately slow. In this case, this is pretty slow with the 2,500 neural network we added as NN2. But you can see we're ploughing our way down from where we ended last time, roughly. It leaps around. The cost curve is a bit jumpy because I haven't taken the random component out of this chart. And it's a pity that it's not updating as we go along, because I would have enjoyed seeing what was going on. But if I just Alt-Tab, I thought it might give us an update on the screen, but it didn't. Iterations is obscured. We shall see where this ends, and I'm reluctant to pause the video, given that you've probably been staring at this, if you have, and I'd be quite amazed if you had, for as long as me, and you might want to see the result. So, okay, the loss curve, I changed the sign on the loss curve. You notice on the first curve it went up. I just put a 0 in front of the cost function. I think on the loss function I should have had a 0. I think that should be negative, because you're trying to minimize it. If I fixed the red dots and stopped making them random, then would it learn more slowly? It wouldn't learn as perfectly, because it would be capturing the actual data that's there, not necessarily the circle representation that we're trying to get at. But such is life. This is so desperately slow. I'm not sure I can wait, but I am keen to prove to you that it works. So let me pause the video and show you what comes out of 1,000 iterations. Why don't I add an iteration count at the top for the next time? That would show you what the iteration is, what iteration it's on. Ah, superb. So it got quite a long way there with a learning rate of 0.2, but it was very slow on this computer, agonizingly slow. But if you extend the number of iterations, run it for a long period of time, it'll ultimately learn that circle perfectly. And that's it. So what we did was we had some dots, a red circle and a black circle. We built a neural network to learn from those and try and find a way of learning the function that splits red and black. And then we copied that neural network and we looked at what was learned. We used the copied neural network to color the tiles, the pixels, to make a boundary diagram, and we used the dots to learn. And there ends this incredibly long YouTube video about how to build a neural network. Please, if you would like to comment, I'd be delighted to hear of any slow Excel maneuvers I'm doing, because I use a lot of Excel, but clearly my learning rate on Excel has really declined recently. So there's got to be a lot of quick ways of moving around the screen, filling things in, etc. If you spot some, I'd be delighted. And if you'd like to talk about neural networks, I'd love to engage with you. I'm currently working on quite an interesting convolutional neural network, which I'm just learning with Andrew Ng. And I've got some letter classifiers and digit classifiers with full optimization and batch runs that I can also discuss on this. I think Excel's a great way to learn neural networks. It's very transparent. Enough. Signing off.